let's. Look at the participants panel to make sure that we all can get in.
Kirk.
Start whenever you're ready, John.
Okay.
Top of the hour still.
All right. So are we live now?
Live now, John.
Great. All right. Welcome everybody to Dialogue 2, part of the Barnes Group Advisors Summer Leadership Series. Today's discussion is around qualification for production and the path to additive manufacturing industrialization. So qualification, skills, and trust, some things that we don't often always put together. Today, I think that this is a pertinent topic that's come up a lot. We've got an excellent panel representing a value chain. We've got Jill Christner, Anjani Achanti, and Jonathan Meyers. And I will let you all introduce yourselves. Jill, do you want to kick off the introductions and maybe tell us about your first exposure to additive manufacturing?
Sure, thanks, John. Thanks for having me on today. So I think I'm Jill Christner from SLM Solutions, and I have the honor to lead the North America team here for our team. So my first introduction to AM was schooled on the fuel nozzle, but I think probably the pivotal moment for me happened at IMTS. I kind of grew up in the traditional supply chain with punch presses and lathes, and I was in that portion of the IMTS, and there was the sounds and the smells that go on with that, and moving over to the additive portion of it and seeing this isn't an incremental step in old equipment. This is a completely different approach to how we would manufacture, and things are going to be different forever now when we look at things. So,
interesting. Yes. Your comment about the sounds and smells of IMTS tend to let the mind wander a bit. Throwing it overseas, John, do you want to introduce yourself to anybody that doesn't already know you?
I'm sure loads of people don't know me. Hi, so I'm John Meyers. So I'm the Chief Product Officer at APWorks. We're a spin out of Airbus. And maybe just to give a flavor of when I first came into additive, I joined Airbus straight out of university, and I think it was probably my first or second week. I was sent to a meeting as like one of these graduate engineers, and they were all talking about ALM, and I had no idea what was going on. So I did what you do, which is I kept my mouth shut, pretended I knew what was going on, and at the end I asked a very friendly guy, you know, what are you talking about? What's this ALM? He said, well, additive layer manufacturing. Come with me, I'll show you. And the guy was Trevor Ilston, who's now at Siemens, was previously at Material Solutions. And he took me down to this dark house. And in the back corner, there was a 3D Systems Hughes, so a selective laser sintering machine processing polymers. And I must have stood there for half an hour just staring through the window at this thing recoating and melting. And Trevor introduced me to Dan Johns, who's now the CTO at BMIT. And yeah, I kind of, my whole career track changed at that moment. I was like, this is so cool. I want to do this. So I went from wanting to be, you know, a chief engineer of an aerospace company to going, I want to do additive manufacturing. And I haven't really looked back. I just spent the next few years working my way out of the aerospace and into the AM bit. Yeah.
Great. Anjani.
Thanks, John. So good morning, everyone. And thank you, John, for hosting this. So much value for us in this business pursuing additive. So good morning, everyone. My name is Anjani Achanti. I lead the Additive Manufacturing Technology Center for Baker Hughes. Baker Hughes is an energy technology company providing products and services to the oil and gas services business, but well beyond that in the energy industry. And our typical customers are the big oil companies. Maybe that gives you a sense of what we do, but anything from oil field equipment to turbo machinery to downhole services related products are all part of what we do, products and services. For me, additive, as an engineer, I got exposed to additive long time ago, but in the sense of rapid prototyping, non-metal, just print it out, see how it looks, check form, fit, and function. But a few years ago, having been with the company for almost 14 years, just a few years ago, I would say 4 years or so, I was asked to pursue metal additive manufacturing. And my first question was, does it work? I was asked to take a new role and I said, what is this? Does it work? What am I getting into? So I was very, very nervous when I got into this. And the fact that we are now putting parts downhole in service is just a phenomenal evolution for us, but also in the industry, just seeing how the possibilities today is mind-blowing to me. So that's my entry into additive.
Interesting. Well, mine's very similar to John's. As I always joke, I was the least valuable engineer at Honeywell. So they put me on the Sandia National Labs project, which was scientists leaving the lab, and they'd come up with a process, which is we now know as the lens process. So this was when it was still at Sandia. And Sandia is a fantastic place to go because you can actually go see the nuclear hand grenade. You can see nuclear missiles, the prototypes in the nuclear museum that they have there. So it's a pretty fascinating place to go. And it certainly was something that just lingered, throughout my career. And I was thinking about this the other day that I've played with just about all the different forms of additive, even before we called them additive. So I don't know whether that just makes me old or I need to focus. I'm not sure. But so I think we've got a good panel to talk about this subject. But first I want to recognize we've got two sponsors for today's session. One is the Purdue AM certificate, so you can go online and get trained up in additive manufacturing. Certificates offered by Purdue. It's created in partnership with TBGA, and we're also the instructors for that. And then also Neighborhood 91, which is the production campus that's going up in, specifically with additive manufacturing in mind, in Pittsburgh at the Pittsburgh International Airport. So having said that, last year, Kevin Slattery and our team wrote a blog on qualification and certification. And, and I think today I kind of joke with people that people use qualification and certification like it's all one word. And on the one hand, we know what it is, and on the other hand, I'm not sure we know what it is. And so it's a hard subject, but it is a solvable subject. So I'm curious to get your thoughts on why do we think that this has to be so difficult? Is it just because it's involved, or is it because it means different things to different industries? And maybe John, we'll start with you because you've got your hands in a couple different areas.
I think fundamentally you've got the main barrier you've got to overcome is to be able to, write a specification for what it is you can achieve and demonstrate that you can achieve it consistently. That's kind of the crux of it in the end. The challenge quite often is getting everyone to agree what that specification should look like, because you have lots of different stakeholders involved. And in the case of certification, you have bodies with authority who have to agree to what that is. And in every case, you normally have a customer who also wants to put their 2 pennies in as to what that needs to be. And I think it comes down to today, we're still in a situation where there's a lack of consensus around standards. And so therefore, there's a lot of people trying to figure out what should be in that spec. And for companies like us who work with many different customers, that can be challenging because different customers have completely different ideas about what the spec should look like. And we have to try and satisfy all of them. So I'd say that's, at least from my point of view, the challenge of that process. Yeah, it's a lot about specification.
So Jill, what about you? You also, I know Anjani's got a perspective on this, but I think I want to save it to last. But you would also deal with people who have qualified machines and processes, and yet it still seems to be a struggle.
John, so I think if you look at on the process, right, the machine's a portion of the process, is an X in the get into the Y. And so, you know, the things that we would put in place from an OEM to make sure that you have consistency from machine to machine, and then also in the qualification for, you know, feedback from our customers, it being key that you have the ability to get in and look at and have an open architecture to be able to go in and set those parameters to get you on a path to your qualification and be able to lock it down to where that's at. So.
All right, Anjani. So.
I'm just, it's a very valid question. Why is it so difficult and complex? Here's my take on this. I think we're at that stage of the evolution of this technology where we kind of know what it's about. And now we're talking about putting parts in service across different industries. So we've got everybody curious, excited, and the proof points are there. But to move into mainstream production, some other questions come up, right? Does it work? Does it work safely? Is there a performance risk? Is there a safety risk? So all sort of pertinent questions are coming up now that it's no longer for prototyping or product iteration, design iteration. It's for mainstream production. So I think that's where the questions are stemming from. And then as people are learning, while the technology is evolving, people are getting caught up one after the other, not together, right? So the standards, I threw in another word, you said specifications and certification. So I think the questions are around, what are you doing? Are you able to repeat the process? Is that adding any risk to our operations? How will I mitigate the risk? Or is it just a one-off supplier telling us, you know, what they're doing is phenomenal? Are they able to make it work every time? But then the conference comes in industry certification. Like, okay, everybody's doing it the same way. It works every single time. And these minimum properties or if these minimum requirements are met, we're okay to deploy this. So I think we are learning from each other and building confidence in each other, at least in our industry. So no one knows whether those documents, those certification requirements are adequate, but we are piling on as we go. And then how do you catch up as a supplier? Where do you stop and say, okay, we meet this and this is adequate? So what's also happening in parallel is we're getting data, having deployed parts. So that's adding to this conversation. But in general, I think that's where we are. It's a long answer, but it's just an evolution. I think people are learning what's adequate, what's not adequate, and just figuring out how to use it and where to use it.
How much, I'll use the word disconnect, is there between like your end customer and the actual capability that you have?
So that gap has shrunk quite a bit, but more so because of us taking an active stance in educating our customers, for lack of a better word. So we invite customer conversations. We just had an internal additive symposium. Internal meaning across all of Baker Hughes sites, but we did have some guest speakers, such as our customers, talking about where their needs are, where their problem areas are, whether it's lead time or innovation or just functionality, wherever the benefits of additive are. And so I think that gap is shrinking, but they have questions around process repeatability, quality assurance of the parts, and some other capabilities that we may not have it yet, but we're getting them to ask the right question. They're interested in DED processes, for example. So they are understanding the limitation. They know where it works. We're getting good questions from our customers. So that tells me that their own knowledge is improving, and they know where the technology is most applicable.
Yeah, and that's kind of a different thread. I wanted to go down the standards path for a second, but I think that you touched on DED, and so oftentimes, where we sit, additive means like one thing, but that one thing is entirely irrelevant to somebody's experience. So additive is very tribal in my view. You've got laser people, and you've got e-beam people, and you've got powder tribes, and you've got, you know, people who've grown up with different additive technologies, but, you know, rarely does there seem to be a cosmopolitan group that appreciates DED for what it does and powder bed for what it does. Are you, what if,
There are some of us, John, some of us appreciate all these things, but yeah.
yes.
So I just want to add one more comment. I know I talked about DED, and your question was on standards, John. So what's happening with our customers is they're willing to participate in industry JIPs. They are bringing these conversations to certification bodies such as the NACE committee. So they are actively present in these forums. It's API committee, ASTM work groups. So we are getting more and more comfortable on the standards and certification requirements that they are providing their input. Not all of them, but the big players at least. I can't recall what your question was on the DED side, but
yeah, it was really just a reflection of, you know, how many, you know, what's the universal level of appreciation of additive?
Yeah.
Or is it, I understand this really well and I think I'm an expert, or is there really the appreciation across the board? Because, you know, anymore, there's all these startups and they don't fit the traditional definition, you know, that we're seeing, which is fine. I don't know that that's an issue, but
I think
it does mean people who grew up with plastics, they seem to think that that is, you know, the sum total of additive, whereas other people grew up with one technology and they stuck with it.
Absolutely. So I think what I see more often than not with our customers is they really understand the powder bed laser process very well. DED conversations are just starting. There is some understanding of binder jet for tooling related applications, but beyond that, not much. So if you think about all the ASTM defined processes, very few people are aware of all of them. So we do a lot of internal education, and with your support, we've done several of these training sessions. But until you show them on a slide that there's more than one process, I think very few people think of those other processes.
John, you were going to say something.
I was just going to say, I think you bring up an interesting point there, John, about how many different processes there are, because I've always had kind of this challenge with that you get a lot of like myths and legends, which kind of, and sometimes truths, but out of context. So people will hold something to be true, which is true for one technology within this realm of additive, and then they'll misattribute it to another technology. And I think that's can be a big problem when it comes to, again, writing standards and so on, because you get people repeating stuff that's wrong out of context, and it starts to become like it's just there. Everyone thinks that there's, give you the example, your oxygen pickup with EBM, right? Mm-hmm. Definitely needs to be monitored. You need to measure it. It's manageable, but you need a very clear protocol in place. Oxygen pickup with laser beam melting, much less of an issue. There is an oxygen pickup, but it's at a very slow rate, and actually it's orders of magnitude different. So you can handle that in whole different ways. But there tends to be this conflation sometimes between the two. And it also depends a lot which alloy you're talking about, how sensitive it is to oxygen or hydrogen. And all of this stuff kind of gets, we actually have thousands of different things. If you talked about specification, we're talking about thousands of specifications. If you actually tried to specify what everyone is trying to put under one umbrella today of additive manufacturing. And I think we have to start being more precise about what we're talking about. This material, this process, and I think that's one of the issues we have today. There are so many that it's really hard to get people to get focused on one and get it right, and not bring in any of this junk, you know, from the sides, which is not helpful.
And just to add on,
go ahead, Jill.
No, I was just going to say, in the different pockets that we see, then we start documenting for what we know in that piece of it, and then we have sometimes the standards or the specifications get pushed back, where we try to make a specification that may limit the technology of what you may choose or the advancement of the technology. So it causes confusion around, because I applied it to this, now it should, and within my industry, which may be very different when you take aerospace versus a medical versus, say, oil and gas versus automotive. And then we try to just put a bow on it. It's not quite there yet.
And I think this is the difficulty with any emerging technology, is that there are a lot of levers to this process. So it's generally good to kind of leave some of them alone for a little bit, but then we tend to believe then that those levers are no longer available to us. So powder is usually the one that I pick on because it's one that I know well, which is, we all know that 15 to 45 is magical, 15 to 45 microns. We all know that laser powder bed falls apart if you go outside of 15 to 45, just instantaneously explodes. So, but I think all the specifications then reflect that. And then where do we go? So I think on the one hand, it's great that we're having the conversation to have the specifications. But then on the other hand, in some cases, I feel like maybe we've rushed into them. So I don't know what the right answer there is. I think it's probably better to have them than not to have them.
I think there's an interesting point there. You talk about, powder size range as one of those things. I mean, I think the other point is what are we trying to standardize on? Because there are so many trade-offs involved in defining a spec. You're trading, generally speaking, performance factors versus cost factors, and every industry has a different trade-off to make. And when you get really in the details, some industries are very obsessive about, one material property, which might be very important to them, but not to another. And that's where I think we're still at that early phase where you've got differences from the bottom and the top, and it's challenging. We're just tying them together where we can, I think. That's the point. Yeah.
So let's see. I wanted to transition a little bit. So one of the things, at least in aerospace, which is where I kind of graduated from, and we talk about the building block approach. We talk about the systems engineering V. It's a very consistent, and I don't, we can attribute it to aerospace, but I'm sure it exists in other regulated industries. But it's the matching. You start with coupons and you validate some of your analysis, and you go to sub elements, and you gain, basically it's a way of gaining confidence as you go and get bigger. With that in mind, I mean, that's a building block approach. It's tried and true. It builds confidence and allows us to keep on moving. The one thing that it holds out, though, is this marriage between the ability to what I can do, what I can design for, what I can analyze, what I can inspect. And I guess I've underappreciated that piece outside aerospace. Maybe one industries that really don't do much inspection, or the inspection is something entirely different. But John, you brought this up. I liked your analogy of the Bermuda Triangle. Perhaps you could explain what you mean by that, and then we could have a bit of a discussion around that.
It's just one example of one of these trade-offs that's hard to resolve sometimes in organizations, is between, non-destructive inspection, materials and process specification, and stress analysis methods and tools, and how that's applied. It's the defect problem. So let's say, well, we start with the materials and process guy says, what defect should I put in the spec, right? It needs to be what you can detect. So we ask the NDI guy, what can you detect? And the NDI guy's answer is, I can detect whatever you want. How much money do you want to spend? Basically, pretty much within reason. There are going to be limitations. Let's say, look, what do you need to find? And then he'll ask the stress guy, what do you need to find? So, well, it depends. What can you give me? Because each person has different incentives pulling on them. And generally speaking, coming to a consensus on what is a critical flaw size, the stress guy needs to understand the effect of the defects and decide it's a trade-off. It's always a trade-off. What is the effect of the defect? What is the probability of occurrence of different types of defects? So what's your scrap rate going to be on the materials and process side? And on the NDI side, what's your probability of detection going to be, depending on which NDI method you apply and how much that's going to cost you? And it's got to be a balance that's made between those things. And I'm just talking about one line in a spec. And you've got to get all those people to agree on something where there's no right answer. There are just answers. There are better and worse answers, and it all depends on your perspective and your trade-offs between performance and cost. And that's why I was coming back to that performance costing. And I'm sure there are millions of other Bermuda Triangles in the spec. They're probably all over it. But that's just an example I quite like, because I struggled with it for quite a few years.
Anjani, is there a Bermuda Triangle in oil and gas?
Well, yeah, completely resonates with me, whatever John shared, because we're looking into all of those same aspects. We put a CT scanner next to the printers to try to figure out what to look at. And we're using defects to make sense out of, okay, what is a critical defect and what's a passable defect, and how do we figure that out? We're trying to apply machine learning to some of this data to tell us the answer, but there isn't enough data. So we ourselves are there. And of course, what you don't want to do is detect defects after the fact. So real-time defect detection is high priority for us. We just want to make sure fail fast method, right? So we are probably overdoing a bunch of things, not knowing what the optimum route is at this point, but also collecting data in that process to see what the effect of those defects are. And it's such a geometry, part specific, application specific issue that we just build our knowledge as we go, and each becomes a case study. But until we get to that point where there's enough data to say green light, red light, we're going to keep doing this the hard way, I think.
It reminds me of, there was a chief engineer at Pratt & Whitney, and his quote was, "In God we trust, and everybody else brings data." Which I always felt was very appropriate for engineers. That should be the way that we travel on data. So let's see. I think before we leave standards, there was a question. There's a couple questions that has come in, which is around the standards development, and it seems like we've got a lot of. There's two ways to look at this. There are those professional societies that have out there, all providing standards. Do we need a single body? Do we need coordination? Because each of the requirements for aerospace are a little bit different than the requirements for oil and gas, which are different than medical, which are different than automotive. So it does strike me that having let's say the standards organizations or the professional organizations that specialize, having them go down this path is a good thing. But then it's only a good thing if we all have access to good information. Is there a need for a single organization, or is there really benefit in in this diverse path? And maybe Joe, I'm going to throw this one over to you first, because whatever happens, I think it's beneficial to the equipment manufacturers broadly.
Yep. So John, I'll answer that to have one. That's the easy way, I think. But I think it does have to be diverse a little bit, going back to what we talked about previously with everybody's coming at it from the experience that they have in whatever industry that may be in. And so to push what they know and put on the table what they know, and then to be able to pull it all together, because what the aerospace industry needs is a bit over here. What a tooling industry may need is very different, but the standards have to be able to meet whatever industry that we're playing in.
I would agree with that. I think we already mentioned that it's very application specific, and there are new or different constraints for us compared to aerospace, and there are some that we may not want to deal with or want to address that aerospace does. I mean, we are, for example, hipping of parts is not something we're looking at for various reasons. So I think it has to be industry specific, and our customers are asking for that. They require that. Until we build some confidence over the next few years, there's going to be more questions, and there's still a tendency to compare with current material, current standards, current specs. How does your additive material compare? So if we don't break those doors and prove that it's equal or better against the traditional standards, we're going to take longer for acceptance. So I think it should be industry specific.
I'm going to sit on the fence and say it depends, but the reason I have is I think these things always work themselves out eventually. That's how economics works. In the end, it's a trade-off. If you standardize something broadly enough, it tends to get cheaper because you have bigger supply chains with less bureaucracy. But they become less specialized and less well suited to your application. And it just goes back again to that trade-off between, you have to decide how important is it for you, the trade-off between the cost of the system that produces the thing you want and the specific performance of the thing you want to kick out of that system. And in the end, there will be a balance will be found. There will be niches of specialization with their own specs where it's worth it. And there'll be other areas where we'll live with general standard specs because it's just not worth being more specialized than that, because it does the job well enough and we get volumes and economies of scale. I think it's unfortunately no simple answer, I'd say. It's just.
And is it fair to, so I've told people that, you know, when they say, oh, well, you're from aerospace, you know, you don't understand automotive. And you know, my common answer to that is, well, you know, okay, when a system fails in aerospace, it means a certain thing. But if you have an inherent flaw in an automotive system and you fail 1 million times a year, then it's a different consequence, but it's still not good. You know, it's a financial consequence maybe versus a loss of life. Either is unacceptable. So it's, you know, it's 6.5, one dozen the other. It's really the details of how you're going to approach it that matter. And kind of this is where I think additive gets very interesting. And we've kind of touched on it, that it is a little bit multidisciplinary inherently. It isn't just one thing. So Anjani, you brought up hipping. Okay, well, aerospace uses Inconel 718 and oil and gas uses Inconel 718. But if you're hipping it and they're not, it's not the same microstructure, it's not the same material. It's now taken a separate path at some point. And I find the same thing's true with the various processes. So I think a lot of people are familiar. So the good news is for Jill, her industry's done a fabulous job of telling people that laser powder bed fusion is the way to go. For the other more emerging technologies like binder jetting, you know, that's really a more process driven. It's a little bit less about the printing, although the printing is important, but the process afterwards is much more critical than maybe laser powder bed fusion. Is that a controversial statement, or do we all just violently agree?
Yeah.
For me, John, it would go back to kind of what we talked about earlier. We get a technology and then we get comfortable with that technology, and then we want to focus on the positives of that particular technology versus saying this technology works best for this application. And yes, this application can use different technologies, but going back to what application are you after, maybe what volumes are you after, maybe what strengths do you need, but in the end application, what would be the best technology to align to what you need in the end?
Just to add to that, I think this is the year where most of us, every one of us, is facing tremendous cost pressure. So for us, the economics is a big piece of what drives the choice of the technology. I think with powder bed, the more mature process, the drawbacks are the cost, as it, you know, from our point of view anyway. So binder jet is opening up some possibilities as a substitute when it comes to cost reasons, but again, it's application specific. There are some other factors, size, you know, operating environment. Just to comment on the previous question as well as this, we're talking between industries, but within our industry, within our company, the needs, the operating environments are so different that, you know, it's hard to look outside the industry for us. We are facing so many different variables within our company and within our industry. So just with that in mind, I think the process selection for us is based on the functionality of the part and the cost target that we are after. This year, we're looking at binder jet more for obvious reasons.
I think that's a good point. I mean, even within aerospace, there is, I will say, there's no universal agreement on things. I mean, we between the Air Force and the Navy, we don't even agree how to refuel planes. So when it comes to damage tolerance and very specific things, you know, how we define that, it can be different by the services, it can be different by the aircraft manufacturers. But, you know, we get harmony at the level of like the FAA and the EASA level because there's good reciprocity there. But it means that they both have to be coming along on the journey. nobody likes surprises is maybe a different way of saying it.
John, I'm going to skip back to something you said earlier, but it raised a point to me that I feel is not an often misunderstood aspect of AM material selection qualification, which was, you said about, okay, you've got Inconel 718, hips, not hip, they're different microstructure, different material, essentially. The number of times I find people saying that, wouldn't it be better to use like a stock material like 7000, 7075 on the printer because, you know, that's a well understood material, so that'll be easier. The point is, as soon as you put it through a different processing route, it's a different material. And I think often people don't realize that, you know, that really there's a hell of a lot of work to do to qualify a material, and starting with the same chemistry, it might help you in a few areas, but it's not going to take away the bulk of the work. You've still got a mountain to climb. And I think that's something that's often misunderstood. Like, it's Ti 6.4, therefore it's Ti 6.4 easy. I mean, the main benefit of using Ti 6.4 is the feedstock is more easily available. That's about it, actually, I would say.
Yeah, that has been a legacy difficulty with any new process. You know, if you know, I remember having a discussion 10, 15 years ago with some of the team at Lockheed saying, you know, to that point, shouldn't we just go ahead and start using Ti 6.4 with boron, because, or just Ti with boron, because that's going to get us to where we need to be, which is, if our true destination is drop-in replacement,
yeah,
via allowables, that's maybe the way to go. So we talked about processes, we talked about details, we talked about multidisciplinary teams, we talked about microstructure, which is one of my favorite things. You know, in this geometry component. So Anjani, you touched on it, but I think there's probably a lot that we could draw out from that, you know, which is, in additive, the geometry that you're making in some way dictates the properties that you are then going to get back out. So when we cast things, when we forge things, we put minimum thickness or maximum thickness on them, and then we have properties associated with it. Can you talk through how you see geometry maybe being a little bit more difficult, but again, solvable?
Yeah, so I'm thinking of an example. So I think it's common practice now that people print witness specimens that go along on the build plate with any geometry. I'm talking about powder bed laser process here. So we've realized that how you set up the build, how you nest parts, how you orient parts, the supports, everything is a factor in how the part performs. So what we're starting to do is get specimens off of the part as part of the qualification to be a better representative of part performance versus maybe relying on specimens in you know, standard specimen shapes and sizes in one corner of the build plate. So that we feel is a better representative for any kind of post-processing. But also this is where we're pushing for real-time melt pool monitoring, or near real-time. So that way we know what's happening at every layer, every feature. We're able to analyze, we're wanting to analyze those images and draw some intelligence out of what might compromise a part at a certain location. So there is in-process monitoring that we think will be the key to address that variability that comes with geometry and shape and build setup. But then there's also specimen collection at the right location, provided that's an option that we're trying to do to mitigate this. Does that answer your question?
I think so, and I think you touch back on the, you know, with the in situ monitoring, you know, that in itself is a journey, and it requires validation, you know, in and of itself. So we're on that. Sounds like you're on that path. Other people are on that path. When we talk about the equipment, you know, there's kind of two schools of thought there. We started with this thought that, you know, having the thing locked down was the way to go. Companies spent a lot of time, you know, singularly focusing on the powder, the parameters, and therefore it was going to give you hopefully the same answer every time, depending on what question we were answering it, versus, you know, a more open system, which are now out there. I know Jill's answers to this probably, but I'll get to her afterwards. So maybe Anjani and John, what's your take on this?
So we, as you know, when we talked about what Baker Hughes is doing, we're still trying to lock down powder process parameters and post-process parameters. What we are learning is that there are other variables beyond that that could change and you may not even know. The machine condition changes. All these other three things that you're holding constant might not be enough, right? You know, might look like they're enough, but we're realizing that no two parts coming out are identical. So what we've done is tried to stay above a certain minimum, well above that minimum. So we know that every single time we're meeting our minimum requirements. So that's been our approach so far, but we're wanting to do some cool things with the machines, now giving the possibility that you can significantly increase your productivity if you play with the hash strategies and come up with a way to retain your material properties, get that same microstructure, but produce parts very, very fast. I don't know, 150 micron layer thickness, but somehow if you can figure out a way to print a part equally good, but very, very fast, that's very, very attractive for us. So we're looking to explore what the machine can do and then keep it consistent across the build plate, but just on the forefront, I mean, just at the beginning of that at this point.
John?
So I think, I think with the machines, there's a lot said about, you know, fixing input parameters. We mentioned before geometry is like the biggest variable and you've got a lot of interactions. The analogy I'd give is, you know, if you're driving a car and you want to analyze what's going on and all you do is measure the position of the throttle pedal, right, of the gas pedal, US, there's a hell of a lot you don't know that is changing around you and changing with time as well. And that's the same with an AM build process, right? You would actually need to know what revs is the engine running, how much torque is there going through this, which gear are you in, what's the slope of the road, all of that to determine how fast that car is going. And same with AM, you have what was the previous layer, what was the layer before that, what's the, you know, the heat conductivity down into the base plate, what's the base plate temperature, how long has this build been running, all of that stuff. And essentially what it goes back to is we need to be able to measure the right thing in order to be able to make it completely geometry independent. And that's essentially what's happening at the melt pool level. So I think that's what Anjani mentioned.
Yeah.
And I think today we work, you know, we have quite a safe envelope to work in. You can characterize an envelope that works. It's again a question of optimization. So it's all about how far do you want to push this in terms of like going faster, therefore reducing cost, and how much do you want to squeeze your properties at the other end of the spectrum to the highest possible level. But in terms of having something that works, which is what most people care about, I think you can do it. You know, well, we've done it. We've done process qualification for TIE 6.4. You can do it, but you need to put some sensible envelope on things. You can't, you have to fix a lot of stuff. You put a sensible envelope and you don't set your, you know, your requirements at the level just a fraction below what you statistically achieve. You give yourself a bit of buffer and safety margin. And I think that's the, you know, it's a pragmatic approach. And then in the future, you go towards optimization. But today we just go for safe, right? Safe, taking into account all of those things. And if anyone wants to know why geometry is the biggest variable, I recommend Googling EBSD and try and find some plots of electron backscatter diffraction plots for additive parts. The grains, it gives you a real nice insight into how the microstructure changes depending as the grains grow through the part because of the way the part is built. And if you build the same geometry in a different orientation, the grain structure is going to be completely different. And it's different in thin walls and thick walls. Like I said, you can envelope all that nicely as long as you understand what you're doing and you can be cautious. But if you maybe naively go for the best results you got and try and write a spec around that, you're going to run into problems when you start to go into real geometries. And that's, let's say, where experience is really important, I would say, is to know your limits and understand all those other things you've got to encompass in the spec to be safe. That's the key.
Well, and I would just tack onto that point, you know, with the grain size component, and it's a different answer. It's a different answer in tie than it is going to be in aluminum because of the way that metallurgy works is very, very different. Yeah. So there's a reason why people tend to specialize, you know, in certain areas because the knowledge doesn't necessarily transfer.
Yeah.
Just one more thing.
Oh, sorry.
Sorry. One more thing to add to that is the machine itself, the machine design itself, right? Different Machines are designed differently, and we are trying to make our center machine agnostic. So our methods are, are there to address that variable as well. Which way the gas flows, what some potential blind spots might be for one machine are not the same for the other machine. It has nothing to do with the three things that we were controlling. So we're learning that it's very important to be above that minimum, well above that minimum, anywhere in the build chamber to account for all of these variables that we may or may not realize are occurring over a period of time. And that period of time could be very short too. So just to add to that complexity. Back to you, Jill.
Yeah, no, it's always fun for me to listen to the different perspectives. So for, kind of for our equipment, right, we very much, it's one of our pillars that it be an open system, but open doesn't mean that we have expectation that a customer immediately starting out has to figure everything out. It's really around, you're offered a system that you can plug in and begin printing your parts, but then you have the ability to go in and dial things in, and that really, we believe, is what can launch you then into your most productive, best business case, to get you through the qualifications and then be able to lock that down to get repeatability and reliability.
So I think what I heard out of that discussion, it was that you have to start with something that's fixed and known and good. And then there's an ability to tailor it and eke further performance, whether it's cost performance or technical performance out of the system based on thicker layers or different types of things. So I don't know. Personally, I thought it was a good discussion there. I'm gonna pause now and we've got a question. It's trending. I'm using my best TV host personality. Personality is not the right word to use. What role will take process monitoring, process tools to support part certification? Is that being taken into account in the current specifications under development? So maybe what I think the question is asking is kind of the current status of process monitoring tools. Are they being used in part certification? And are they being taken in, are they then a given in some of the specifications? So the specifications that I get involved with, mainly on the material feedstock side, so a lot of that doesn't include it. Maybe John or Anjani, you can comment on whether people are using these tools. Process monitoring, first of all, is a pretty broad topic.
Sure. So if you're talking about milk pool monitoring of the process, I would say that we're not seeing those in specification. I think people are still trying to figure out what to do with that data. So that's where we are. And we're partnering with some third parties to figure out, okay, we know how to collect the data. What do we do with that data? That's where Baker Hughes is. But we believe that is going to be the key to quality assurance, a big piece of quality assurance.
Yeah,
John?
I'd agree hardly with that. I think there's a lot of machines are having these systems put in. So the hardware is there, like our machines have the hardware for at least for camera systems and so on, which is really useful. A lot of defects originate within recoating or support failures leading to recoating issues. So even a basic camera system can be very useful. The challenge is, how do you interpret the data? That's the big challenge. How do you know when you see something with one of those systems, whether it's looking down the laser and generating, I don't know, gigabytes of data per second, or whether it's just a camera system just generating gigabytes of data per build, how do you interpret that data to know what that leaves in your part? I mean, this is something we've done our own developments in-house actually. So we analyze every build from the camera system, and we've written some algorithms to correlate between what we see in the pictures and what we've seen in CT scans. We've got lots of data available. But that's not something that's widespread available, hence it doesn't appear in the standards. It's kind of a dream that at some point this will be widespread, understood. And the biggest risk, just to say that I see with those systems, is false positive indications. So the AM process is actually quite tolerant of issues. And what you see in one layer, you might not see in the final part. You get one bad layer of recoating, and the process often depends on material, process, parameters, and everything else, caveat, caveat, caveat. But depending on what you're seeing, it can have the ability to heal that defect in the next layer. And the biggest challenge then is getting this sort of probability of detection curve for those in-process methods. You have to basically treat it like an NDT method. You have to treat it exactly the same as any other NDI method. What is the probability of detecting what you need to detect? And in this case, you'll get quite a lot of these false positives until you develop the layer on top, which is what we're doing, which is basically interpreting that data with respect to understanding what you actually get in defects. And I think that's, I mean, we're using it for our internal purposes. I think it's got a long way to go before that becomes a standard across the industry, to be honest. A lot of data needed.
So you mentioned specifically there's a lot of data. And I mean, at one point I remember telling my boss 10 or more years ago that this will be the preferred process because we will have so much more information about the part once it's done than we've ever had. Now that can be a blessing or a curse. But Jill, this must present challenges to equipment manufacturers because on the one hand, there are some really innovative, I'll say smaller companies that are attacking a bunch of different angles, but there's many and sundry. So how do you focus on it? How do you decide, what are your customers saying they want versus what's available? And, there's a couple different questions in there, but you can choose the one that you wish to answer.
Yeah, no, John, I think that, the question of you're gathering so much data and what do I do with the data and how do I interpret the data? I think as quick as we can get to that point, it now becomes, how do I fix it before I actually lose the part? So the data is not just telling me, hey, it's wrong, but now in situ, while it's still printing, I have the ability to adjust and fix it. Like John said, that now it's not a fatal error and I can course correct and move forward with it. But it is, and it goes back a little bit to, again, the different industries and the requirements that you have in the different industries and what is, does every design come out to the aerospace requirements? And that's the level that you have to shoot for, and that's the level of data and in situ. But you're right, there are quite a few startups out there, and good for them. It makes us all better and keeps us on our toes. Or how do we, this now is important. Okay, if this is important to my customer, how do I either bring them into the fold and give them the ability to see it, or say, okay, this is tied into too many other pieces of the laser of how it's got to be calibrated and it needs to be part of the machine. So it's again, it goes back to just getting to the maturity level of the expectations that we have.
So we've got two actually quite good questions. We've got 7 minutes left, so I'll be mindful of that. I want to allow you all an opportunity to have a parting thought. So a little warning, come up with your parting thought. One question is, how far are we from a standard approach to characterizing specifically the laser powder bed fusion equipment statistically towards serial production? So maybe Jill, from just broadly speaking, I mean, is this something, certainly I imagine it's people that are asking the question, but how does it rate in importance to your customers?
I would say it's a mix, John. So certainly we have customers who are already in serial production, who they've gone through the certification, the qualification process, and they, parts are going into their production. So a lot of it is in, the level of maturity of the customer and the type of technology that they're looking for. But I think we're close, just given that we do have customers who are already there. But maybe I missed what they were really after in the question.
Well, I mean, there's more specifications. I know AMS has been producing, qualification criteria for this. So, I mean, Anjani or John, kind of quickly, do you have a different opinion on that?
We're writing our own machine qualification procedures because we're dealing with multiple makes and models, and so we're investing heavily in writing as we go, as we learn we're updating that specification, but machine qualification is key. It started off with taking a while for us once we installed it, but we're trying to reduce that time, and in that process learn quite a few things. And our production mix, it's not entirely serial production, it's not entirely R&D, so it's a hybrid mix for us. But sorry.
No, I was just going to say, I mean, one of the things you just said actually was all powder bed machines aren't the same.
That's right.
They don't actually all operate the same.
Yep.
And even multiple laser systems don't operate the same. They don't function the same. They don't do the same thing.
We have two machines, same type, same model, same manufacturer at two different sites that don't produce the same output. And we can't figure out why. So yeah, that's the challenge.
Swap operators and see what happens. That'd be my advice.
Yeah, right.
I'd
John,
agree that the big thing I'd say from the machine side is you know, reliability and repeatability in a production context. You know, the OEE side of things is pretty critical, and I'd say that's still a challenge to overcome. The reliability in production of those machines is still, it's not at the level of, let's say, what you would expect if you bought an industrial, you know, milling machine or something. And that's still a challenge when you've got something that's very capital intensive and you're paying a lot of the money up front. Every hour that it's not working, it matters. And so there does be, I think a lot of the focus has gone into performance. You can see it, quad laser, you know, going more and more productivity as a way to solve the cost equation for the customer. But there are other ways to solve the cost equation. The real cost equation is heavily driven by lowish levels of utilization and also very high capital equipment cost. And I think those are areas that could be addressed as well by the machine makers, not just making sure they always deliver a machine that behaves the same. But
yeah, I agree.
it's the same forever, not just the first qualification. Yeah.
100% agree, John. I mean, that's how we're building our business case on the runtime, right? So ours, it's operational. Ours, that laser is melting powder. So couldn't agree more.
And I'm not saying it's easy, Jill. I'm not having a stab. You know, it's very difficult to make a machine like that that's so reliable. But I'm saying that's where I think the focus has to be. Yeah.
No, I did.
Well,
it's John, because it's not, you know, the machine is one of the X's, kind of what you said. So when you create your business case, it is the whole value stream, and the machine is, yes, one part of it, and arguably it's probably the biggest X in the value stream. However, it is, you do have to look at it as a whole encompassing part of it, but you have to be able to depend on that. We're working hard on it.
Well, and I think the challenge, you know, for Jill is it's the same machine for different industries. You know, so when you go shopping for a car, you know, if you need a pickup truck, you go for a pickup truck. If you want a sports car, you go get a sports car. So, you know, we're not to that point yet. So I think there's an implicit challenge at the equipment level. We've got a couple minutes left. I want to acknowledge one, Tyler is correct. He has said that the machine qualification standards from SAE are still in work. So that's still going. I'd also I feel like I have to acknowledge Tyler's been doing some pretty missionary work on a specification to look at conditioning of powder. So really going into the definitions of what do we mean by recycle versus reuse versus condition versus, you know, versus, which I think ultimately is going to be very important to us for a lot of people. So I don't know how he does it on the one level, because it's a great committee, but everybody's got an opinion. So it's always that difficulty. Where I've heard is a couple things. One is specifics matter. You know, there's specifics to the material, there's specifics to the type of machine you're using, there's specifics to the type of AM you're using, on and on and on and on. It does seem to be an inherently multidisciplinary problem. Now, I can say that because I love working with multidisciplinary teams. It is also a solvable problem. May need more data. We may have to go with a gut feel sometimes. Let me turn it over to you guys for the last couple words, and then we'll talk about a very quick plug. On August 31st, we'll have the third and final session of the Summer Leadership Series on what have we learned. So from the Coen Brothers movie, I don't know, but you know, it's going to be a good discussion. So with that, Anjani, parting thoughts?
First of all, thanks, John, again. This is a great discussion. Just getting to hear from Jill and John changed my own thought process a little bit here, but I was just wondering, this is an idea that I want to leave the group with, that maybe an industry JIP on pooling our data where data is lacking, for looking at these melt pool monitoring tools out there, what to make of the data. That's an important topic for us. And I'm just, I guess, a call for action that we could put our data together, because you need a lot of data for some of these algorithms to make sense out of which one's a real defect and how detrimental is that to part. So I'm thinking more can be done in this. Not enough people have looked at this, but to me, this is the path forward. Of course, there's going to be more than one technique to assure quality, but I'm thinking along these lines when it comes to production and industrialization. Machine robustness is a big topic for us as well, but these two things are on my mind right now.
Well,
what to do with that data, pool our data together. Yeah.
America Makes just put a call out for industry sponsored ideas. So Anjani, maybe that's a way to go. John.
I mean, I guess the main thing, my sort of parting shot, I think firstly, it's really great to talk, and we should all talk more often. It's, you know, we should get together and talk about this, everyone in the industry. Because sharing knowledge is key, you know, to standardization is a lot about what's in everyone's heads, right? And the more you standardize the thinking, the more likely we are to come up with the same standards. So that's the first point. But the other one is, when coming up with any kind of standard or spec, start from the requirements. And I mean the real requirements, taking into account the business case and everything else. And then specify the spec, the minimum that gives you what you need. That's like just golden rules of like writing a spec for something, is the minimum that you need to do the job you need, not the gold-plated one that adds loads of additional burden and everything else. Now, obviously, that minimum may look different for different industries, but I do think we all have to think about that and not go into the easy habit, copy and paste the requirements of the old material spec that met the requirement of your application, and then just say, right, well, we're just going to assume we need to meet exactly that, all boxes. Some of those boxes will have been filled in because they were genuinely minimum requirements, and some will be filled in because that's what you get and you don't necessarily need it. And I think that's really critical to revisit requirements.
Amen. Jill, that leaves you with the final words.
Yeah, so first of all, thanks, John, for doing this. I echo the thoughts of, you know, it's always good to be able to talk it out. I've learned a lot just in the last hour here, so thanks for doing that. And I think, you know, just leaving it here, a part of me says it's exciting that we're here and we have a long way to go. So it's a mix of both, that, you know, progress has been made and the interest in it, and how do we get to the standards. Everybody's bringing something to the table, and eventually we'll sort it all out and launch it for where we need to be. But we've come a long way. Yeah, we've got work to do. But it is exciting, the progress that's been made. And so I appreciate you coordinating all of this. It's been a good session.
Yeah. So thanks to all of you. Thanks for everybody tuning in. Thanks to Kirk and Cynthia at the TBGA technical headquarters for keeping us on air. So with that, we'll bring it to a close, and hopefully we will see you at some point in person. And until then, I'll make sure everybody stays safe, because we would like to do this again. So it's important that you're around.
Keep calm and mask on, right?
All right. Thanks, everybody.
Thank you.
Bye.
Thanks.